Good evening, everyone. And for our project, we'll be recreating and evaluating an adaptive timeout algorithm presented in the original paper labeled an adaptive timeout algorithm for retransmission across a packet switching network and comparing it to a fixed timeout approach. For some background into the project, the initial problem arises from retransmission timeouts, which affect packet loss and recovery efficiency, where a short RTO can lead to unnecessary retransmissions, and a long RTO can result in packet recovery being delayed. So our goal is to improve the network efficiency by dynamically readjusting retransmission timeouts based on the round trip time (RTT) and its variance. By comparing this approach to a fixed timeout method, we aim to demonstrate how the adaptive timeouts reduce unnecessary retransmissions and improve packet recovery in a fluctuating network conditions. In our methodology, we implemented both the fixed timeout and adaptive timeout algorithms using the ICMP pings in a simulated networks with conditions like latency, packet loss, and jitter. We used Mininet to create a simple network topology, sending 500 packets per trial to compare performance. The adaptive timeout algorithm adjusts the RTO based on the RTT and its variance, while the fixed timeout maintains a constant RTO for all packets at 0.135 seconds.
These are the formulas involved in the adaptive timeout algorithm. The first two equations describe how the average delay, represented by Tn, and its variance, represented by Vn, are updated using an exponentially weighted moving average function. These estimates are used to calculate the retransmission timeout, represented by Rn in equation 5, which adjusts dynamically based on current network conditions. The constants A, B, C, D, and E control the smoothing and aggressiveness of this adjustment, ensuring that algorithm balances fast recovery with minimizing unnecessary retransmissions.
Here's a direct comparison of the result between static timeout and our adaptive timeout algorithm. With the graph on the left, we have fixed timeout of 0.135 second, which results in 152 timeouts, whereas with the adaptive timeout, we would result in only 126 timeouts. This shows the algorithm improves the timeouts by a noticeable amount. We ran experiments with different variables. Here we tried values of A ranging from 1 to 30. Here is the comparison of two scenarios with A equals to 30 and A equals to 4. We can see the larger the C, the higher the average timeout. This means as we increase a value of A, the gap between average RTT and average timeout increase. We also try with various C value ranging from 2 to 30. The comparison between C equals to 2 and C equals to 30 shows that the larger the C value, the smaller the variance of timeout. So by tuning A and C values, we can effectively make the algorithm adapt to different network conditions.
Next, we added a delay of 30 milliseconds to both the networks at around packet 200. As you can see in the graph on the left, the static timeout does not do well to uh, interpret, interpret the delay, resulting in 312 timeouts, as you can see the T values all being above the R value. Compared to that, the graph on the right, we can see that the green line is completely above the orange line, which shows that there were way less timeouts. As you can see, we only have 132. Thus, the adaptive timeout algorithm was effective optimization method given the sudden network changes. And in order for the fixed timer to account for this possibility, it would need to set up a value much higher than 0.125, which would mean that it's not as optimal during the base conditions. Next, we try to change the retransmission limit, impacting the adaptive timeout algorithm. And with a lower y value of 0.05, there's a much better balance between RTT and timeout, leading to fewer drops in timeouts, whereas a higher y value increases the timeout sensitivity, resulting in more timeouts, but it can tolerate more network fluctuations at the cost of responsiveness. Furthermore, the testing showed that the gap between the RTT and the timeout value is irrelevant.
As we've seen in the graphs, the adaptive timeout algorithm consistently outperforms the fixed timeout approach under changing network conditions, such as high latency, packet loss, and jitter. This is because it is able to adjust its retransmission timer dynamically based on real-time metrics such as round trip time and its variance. By doing so, the adaptive timeout approach reduces unnecessary transmissions and ensures more efficient packet handling in fluctuating networks, making it more responsive to network changes. The fixed timeout method performs well under stable and low latency conditions, but still performs worse in the adaptive timeout condition. But it truly falls short when faced with network variations, as it lacks the flexibility to adapt, reducing in more timeouts. Next, for some future work areas. First, it will be important to test its performance in modern network architectures, such as software-defined networks and large-scale distributed systems. Secondly, its interaction with modern congestion control mechanisms like TCP/BBR also need to be assessed. Another area of work could be analyzing the security implications of this algorithm. For example, a malicious actor could trigger unnecessary retransmissions and uh, cause packet delays or drops. Lastly, it will be exciting to explore the potential of integrating machine learning into the adaptive timeout adjustments. Thank you, and this is our citation.